Okay, let's get started. Hi everyone, I'm Saujanya. I'm a PhD student at UT Austin. Today I'll be presenting our work RainBlock. RainBlock proposes a new architecture for public blockchains. So RainBlock's architecture enables high throughput public blockchains by allowing miners to execute transactions faster. So this is joint work with VMware Research and Novi and DM Financial. So today's talk is going to be in three parts. For the first part, I will be giving a high-level overview of public blockchains. In the second part, I'll discuss how public blockchains suffer from low throughputs and the underlying I/O bottlenecks. Finally, I'll be presenting RainBlock and our main contributions that enable high-throughput public blockchains. Please note that I'm not going to give like an in-depth overview of public blockchains. It's going to be in as much detail as is necessary to understand the underlying I/O bottlenecks and our main contributions. And also, please feel free to interrupt me at any point in time and ask questions. So with that, let's get started. Blockchains are decentralized databases. In blockchains, servers executing transactions are called miners. Each miner stores a chain of blocks where every block stores a cryptographic hash of its previous block, and this way is linked to its previous block. So this chain of blocks is immutable, and the immutable blockchain stores the history of processed transactions in the system. For example, every block stores an ordered list of transactions, and any block is only processed after its previous block. Now, public blockchains have open networks, as in they allow any server to join the blockchain network and start processing user transactions. This also means that at times, miners can be malicious. Therefore, public blockchains like Bitcoin and Ethereum employ consensus protocols like proof of work. With proof of work, miners compete to create the next block. Once a miner creates a new block, it sends the block to other miners. Other miners first receive the block, verify the validity of the block, then process the transactions, and finally accept or reject the block. Only after most of the miners accept or reject a block, proof of work allows the creation of the next block. So proof of work rate limits the creation of new blocks. And this is crucial for ensuring the safety and security of blockchain. Now imagine if proof of work did not rate limit the creation of new blocks, any miner could keep forking the blockchain, and this would hurt the forward progress of the blockchain. Today, two of the most popular public blockchains, Bitcoin and Ethereum, employ proof of work consensus and suffer from low throughputs. For example, Bitcoin processes around 20 transactions per second, while Ethereum processes around 16 transactions per second. However, centralized transaction processing engines like Visa process more than 20,000 transactions per second. Therefore, public blockchains need to scale their end-to-end transaction throughputs to enable widespread adoption of decentralized applications. Most of the prior work in this space focuses on changing proof of work consensus in some sort of way. For example, using DAG-based blockchains instead of a chain. Then there is also leader election instead of proof of work. And also there is other work that talks about replacing proof of work with alternative consensus protocols like proof of stake. Ethereum itself is considering moving to a proof of stake system. However, orthogonal to these efforts, our work attempts to see if we can increase the throughput of public blockchains without modifying the proof of work consensus. So this work is important because using proof of work as is allows us to retain its safety and security properties. Till date, proof of work is the only consensus protocol which is most widely deployed and used till date. So to answer this question, we look more deeper into how miners execute transactions and create these blocks. With proof of work, Ethereum miners have about roughly 10 to 12 seconds of time to process transactions and to generate a new valid block. So Ethereum miners have two sets of threads, workers and sealers, to perform these two operations in a pipeline manner, which I'll explain now. First, workers process transactions into a partial block. To process or execute these transactions, workers must read, modify, and update the system state which they store on disk. So workers perform I/O for processing transactions into a partial block. Once workers create a partial block, they send this block to the sealers. Sealers solve the proof of work puzzle, and once they get to the puzzle solution, generate a valid new block. While the sealer is generating a new block, workers process the next set of transactions for the sealer to work on. So we observe that if workers can process more transactions in the same amount of time, then sealers will be able to generate larger blocks. This brings us to the main insight of our work. If we can enable miners to process more transactions per unit time, there can be larger blocks with more number of transactions, and this can improve the end-to-end throughput of public blockchains like Ethereum. Further, it also allows us to use proof of work unmodified and rely on its safety and security properties. So the central idea of our work is to make transaction processing faster and thereby increase the end-to-end throughput of public blockchains. Our goal is to allow miners to safely release larger blocks. However, we notice that it is the I/O bottlenecks that limit the transaction throughput or fundamentally limit the number of transactions a miner can execute, and therefore our approach is to reduce the I/O bottlenecks in transaction processing in the critical path and thereby allow high throughput public blockchains. So from our analysis, we see that it's not proof of work consensus that limits the number of transactions in a block. It only rate limits the number of blocks that can be generated per unit time. And our analysis highlights that it is the I/O bottlenecks that limit the block size and thereby reduce the overall throughput in public blockchains. So to empirically show the impact of I/O bottlenecks on the overall throughput, here's an experiment. So we run a micro benchmark using two private Ethereum clusters, each with 3 miners. While the first cluster has no system state, the second cluster is initialized with 10 million user accounts. So each cluster processes around 30,000 transactions in total. And despite using the same unmodified proof of work consensus across both of these clusters, the second cluster has 6 times lower throughput and releases blocks that are 2.5 times smaller than the first cluster. We measure that miners in the second cluster spend about 60% of the time performing I/O. Therefore, with this experiment, we clearly established that it is the I/O bottlenecks that limit the number of transactions per block and thereby limit the overall throughput in public blockchains. With these insights, we propose RainBlock, a new architecture for public blockchains that increases the overall throughput without modifying proof of work consensus. RainBlock achieves higher transaction throughput by eliminating the I/O bottlenecks in the critical path of transaction processing and allows miners to process and verify more transactions in the same amount of time. For eliminating I/O bottlenecks, RainBlock uses a novel distributed sharded Merkle tree data structure, which we call the DSM-TREE, to store the system state on disk. In a geo-distributed setting, with 4 miners spread across 4 regions and 3 continents, RainBlock miners can process about 20,000 transactions per second. First, before we dive into the details of RainBlock, let's look at how transactions are processed today in Ethereum. Ethereum miners store the system state locally on disk. To execute a user transaction, a miner first reads the necessary data from the SSD into DRAM. It then executes the transaction and modifies the data accordingly. Then it writes these changes and persists them on SSD. Once the miner mines this transaction into a valid block, it sends the block to other miners. Other miners also read the data from their local storage, execute the transactions in the block, and modify their system state accordingly. This way, every single miner re-executes the transactions to ensure the correctness. Now, zooming further into how system state is actually stored at each miner, the state is stored using an authenticated data structure like a Merkle tree. Merkle trees provide data along with proofs that help verify the correctness of this data. So the system state is in a Merkle tree, which is then also flattened and stored as key value pairs in a key value store like RocksDB or LevelDB. Note that there are multiple levels of I/O overheads that come because of this design. First, traversing such an authenticated data structure requires reading multiple nodes along the path, which results in multiple random disk IOs. And updating a value results in multiple disk writes. And inherently, using a database like RocksDB or LevelDB has its own IO amplification that it adds into this hierarchy. We measure that to read a single user account, Ethereum miners read 40 to 60 times more data. And to process a single block of 100 simple transactions, Ethereum performs 100 times more random I/O operations. So with this motivation, I will present an outline for the rest of the talk. I will first describe RainBlock's architecture at a high level and discuss how it overcomes these I/O bottlenecks. I will then detail two main challenges that RainBlock's architecture has to overcome to achieve high transaction throughputs. Finally, adding more details, I will walk through the life of a transaction in RainBlock. In RainBlock, the system state is decoupled from miners and is sharded and stored across the memory of multiple storage nodes. These storage nodes store the Merkle tree in a memory-optimized format and periodically checkpoint it on disk for persistence. I/O helpers are introduced to perform I/O on behalf of the miners and out of the critical path of processing transactions. Typically, I/O helpers prefetch the data required for executing the transaction from the storage nodes. I/O helpers then submit the transaction and the prefetched data to the miners. Miners use the prefetched data, the transaction, and execute the transaction completely from memory and update the storage nodes, create a new block and update the storage nodes with the new block. Storage nodes perform these updates asynchronously. Thus, RainBlock miners do not have to perform any I/O in the critical path, can process transactions much faster, and achieve high transaction throughput. However, RainBlock needs to address two main challenges before it can achieve high transaction throughput. In RainBlock, I/O helpers can prefetch data from the storage nodes while miners are updating them in parallel. Therefore, storage nodes need to provide consistency in the presence of concurrent updates. Next, RainBlock architecture also trades off local disk I/O for network I/O. Remember that miners update the storage nodes over the network, and also I/O helpers prefetch all of the data required over the network. Therefore, RainBlock needs to reduce the amount of data transmitted over the network to achieve high throughput. Note that stateless clients proposal from Ethereum also introduced separate storage nodes, but it did not gain traction fundamentally because of the network overheads that it introduced. So to address the first challenge, recall that in RainBlock, I/O helpers prefetch the data from storage nodes, while miners can update them in parallel asynchronously. Further, as miners share the storage nodes, multiple miners can update them simultaneously, corresponding to different blocks that they are working on. To handle this, the distributed sharded Merkle tree data structure, or the DSM-TREE data structure that is across all the storage nodes, it employs a copy on write methodology to update the storage nodes by creating a new copy for the updates. On updates, as I said, storage nodes create a new copy for the modified data, and I/O helpers can either prefetch from the latest snapshot of this data or can ask for a specific snapshot. And once the blocks in the main chain are confirmed, unconfirmed blocks and updates corresponding to the unconfirmed blocks are periodically garbage collected at the storage nodes. Recall that I/O helpers may also prefetch full paths of the Merkle tree called witnesses and submit full paths to the miners along with transactions. However, miners can now, in RainBlock, we allow miners to cache the top layer of the DSM tree as a private in-memory cache. So the two layers of the DSM tree, the top layer of the DSM tree, which is the miner's private cache, and the common shared sharded bottom layer of the DSM tree in the storage nodes, they both can collaborate with each other to reduce the amount of data that is being prefetched and transferred over the network. For example, let's say miners can store the top layer of the DSM tree till a configurable depth, and I/O helpers now, instead of fetching full paths called witnesses, can prefetch only the data that is not present at the miners, called compact witnesses, and submit these compact witnesses along with transactions to the miners. Miners using these compact witnesses and their private in-memory cache can construct an entire Merkle path required for executing this transaction and can execute it successfully. Such cross-layer optimizations from the DSM-TREE data structure reduce the network traffic by up to 95% in RainBlock. Yes?
Do I understand correctly that the miners now have to keep the top portion of their Merkle tree consistent, coherent with the storage nodes?
So it doesn't have to be coherent with the storage nodes. So at any point in time, miners would be working on a particular block, right? And they would be working on this block on top of a previous block. So they always are working on a snapshot, which is also, that snapshot would be coherent with the storage nodes. But the storage nodes would be storing all the snapshots that all the miners would be working on. Any other questions at this point?
Are you going to get to, so how do you, who wins among different versions if different miners are working on it? Okay.
Right, so actually, I won't get into it, but I can talk about this right now. So even in Ethereum, the way which block wins is part of the consensus protocol, right? Eventually, it becomes difficult to create blocks on top of a previous block. So the longest chain or the heaviest chain wins. And we are not modifying the proof of work consensus. So it's the same way it's determined even in RainBlock. Yes, please go ahead. Yes, I would. Yeah.
Sorry, one more question.
Please go ahead.
You're changing now
So actually, it's not entirely true. So miners can be configured in a way where if they don't have a in-memory cache, they could fetch from the storage nodes, right? If miners are allowed to do network I/O in the critical path, if they are configured in such a way, then you can partially move miners to this. You can have a hybrid model where part of the miners can be working with their own, with no in-memory cache, but just doing network I/O, and other miners could be having this in-memory cache till a configurable depth and all of that.
And the former of those alternatives, that's closer to the Ethereum proposal, right? Where they did a lot of network traffic.
Yes, so the question is, how is this work similar to stateless clients proposal? So in stateless clients proposal, what they say is they're going to keep these witnesses as part of the block, and it becomes part of the storage, right? One of the main reasons this would not work is every time there is a broadcast, peer-to-peer network broadcast of this new block, it increases the size of the block and it increases the network traffic. Secondly, because of storing these witnesses as part of the block, you are never going to garbage collect them, right? You're going to store the blocks, and it's going to also put increase the storage bottleneck, right? So for those two reasons, stateless clients was not adopted widely. In our proposal, we have like an in-memory storage for all the unconfirmed blocks, which are going to be garbage collected later. And the blocks themselves are exactly the same blocks as Ethereum has today. So it's not going to increase the storage capacity requirements. Next, the only added network I/O in the critical path, or it's outside the critical path, and it's I/O helpers. And you can scale I/O helpers to as many as you want. Like you can imagine that users themselves are trying to fetch the data that is required for executing their transaction and submitting the transaction and the fetch data to miners, right? So, and you have as many users as there are clients. So, yeah, we don't believe it will be a problem. Yes, please go ahead.
So maybe I misunderstood this, but before you had one miner role processing the blockchain transaction, you kind of disaggregated it into some specialized nodes, storage nodes, and I/O helpers now. My question is about volatility of processing transactions in RAM mode now. You're getting some performance benefits of that. But doesn't that volatility, lack of persistence of these intermediate blockchains bother you? Or potentially I'm thinking of geos where there are power cuts and things like that. How does this impact?
Great question. So the question was, we are decoupling miners into now storage nodes, special storage nodes, miners which process transactions in memory, and I/O helpers, right? So this decoupling is fundamental because we identify that miners are only responsible for ensuring consensus. They should not be responsible for storing, for maintaining storage. If you are doing that, and if you are introducing storage in the critical path of processing transactions, then inherently you are reducing the number of transactions that miners can process. But the question is, now that we have this design, how is it going to affect maybe forward progress or in terms of failure in geo-replicated situations, right? So I always go back and compare it again with the Ethereum ecosystem, where even if miners are working with their own local SSD, a miner could fail while processing. Even if it solved a proof of work puzzle, it could just fail after that, right? Or it could get partitioned from the rest of the network, which is the same as a miner working on its in-memory work and probably like failing at some point after that, right? Only after the storage nodes are updated, a miner is sending that block to the other miners. So there is a a way in which there is a way to ensure that the storage nodes are updated and miners will be able to find that previous block for the other miners to build on top of. But failures will not add any new metric which is not present in Ethereum. So miners are capable of handling those. Does that answer your question?
Yes.
And to handle like the failures of the storage node, we have like replicated, for each partition, we have like replicas. As long as one replica is up, you can ensure forward progress of the system. Okay, let's go ahead. Okay, now I will summarize the RainBlock architecture by looking at a life of transaction in RainBlock. So in RainBlock, miners store the top layer of the DSM tree in a private in-memory cache. The bottom layer of the DSM tree is sharded across the memory of multiple nodes. The storage nodes also store the DSM tree in a memory optimized format and use and only checkpoint it to disk for persistence. The IO helpers pre-execute a transaction to prefetch compact witnesses from the storage nodes. So notice that by allowing IO helpers to prefetch a transaction, we can also support smart contracts or transactions in which the read and write sets are not known beforehand. And they can prefetch data that is required for executing a transaction in whole. Once IO helpers prefetch the required data, they prefetch compact witnesses instead of full witnesses because miners have the top layer of the DSM tree. IO helpers submit the transactions and the compact witnesses to the miners. Miners use the compact witnesses from IO helpers and their private cache to process transactions. Miners then create a valid block, mine these transactions into a valid block, achieve consensus on it, and then finally update the storage nodes. Storage nodes asynchronously create new snapshots for the updates from the new blocks. Once the blocks in the main chain are confirmed, snapshots corresponding to the unconfirmed blocks are garbage collected. In RainBlock, all components, the storage nodes, IO helpers, and miners can work without trusting one another. So this is core, the chief thing to enable such an architecture for public settings where there is no trust between miners or any of the entities. Also, RainBlock uses unmodified proof of work consensus, and it inherits the same safety and security properties as Ethereum. RainBlock's architecture sure adds more complexity and more hardware, but it is in return for much higher throughput and higher scalability. For more details on RainBlock, please do find the full paper online. And I will briefly present an evaluation of our work. So to evaluate RainBlock, we use Amazon EC2 large instances, each with 32 gigabytes of DRAM and 48 threads. Storage nodes, miners, and IO helpers are deployed on their own instances. We use a workload generator to synthesize workloads that are exactly similar to the transactions in the public Ethereum main network. So we notice that to have a comparison point, right, like a baseline point for our evaluation, we use Ethereum single miner. And we notice that a single Ethereum miner can process around 1,000 transactions per second using a single server for hosting this miner. This is the best case scenario for Ethereum, and we compare RainBlock against this baseline. Note that the publicly available number of geo-distributed Ethereum, the number for the transaction throughput for the geo-distributed Ethereum shows that it can process about 16 transactions per second despite using more than 4,000 servers. So in comparison to these numbers, a single RainBlock miner with 1 IO helper and 16 storage nodes can process more than 2000 transactions per second using a total of 18 servers. In this setting, we also notice that the miner is heavily underutilized. Therefore, we scale the number of IO helpers. By using 4 IO helpers instead of a single IO helper, we increase the amount of data being prefetched and the number of transactions being submitted to the RainBlock miner. Essentially, we are increasing the load on this single miner. And in this setting, a single RainBlock miner can now process more than 7,000 transactions per second using a total of 21 servers. Now, we check the performance with the DSM-TREE optimizations, the 2-layer DSM-TREE, with miner storing the top layer of the DSM-TREE as a private cache. So using the same number of IO helpers, we introduce the DSM-TREE optimizations, and RainBlock miners can now process more than 27,000 transactions per second with the same 21 servers. So you can see the impact of network IO in this setting.
And at that point, your miner was saturated.
Yes, with 4 IO helpers, a single miner was able to be saturated.
One question.
Yes.
What's the aggregate IO you're moving to the helper of the miner when you're running that transaction rate?
Sorry, could you repeat the question?
How many megabytes a second or throughput are you moving into the miner or the IO helper at that transaction rate?
So are you asking the number of transactions or the amount of data? A couple of megabytes, actually. So the transactions themselves are not really being moved, right? There is a transaction pool from which the data will be fetched. And the Merkle tree data structure itself, the maximum depth is about 12 nodes, or an average is about 8 nodes. So because of this, it's not a lot of data that is being moved around. But it is, when you think about it as storing it on disk and storing multiple versions of the Merkle tree on disk, the storage space on disk is a couple of gigabytes. But because all the older snapshots can be garbage collected and all, the in-memory state is much more compact, and the amount of data which is being sent over the network is also very small.
For your evaluation, how much of the tree did you cache in the miners?
So for this, we cached around a little less than the average depth, which is around 6 nodes. And each node, so the depth is 6 and the branching factor at each node is 16. And hence the 16 storage nodes. We just sharded one subtree from the root node. Each subtree became one shard.
But for your partial representation of your Merkle tree
Yes.
in the
Miner.
how much of that depth of 6 did you cache?
So the total depth is much more.
I see. So you cached 6.
Yeah, we cache 6. Average is about 8. It could go up to 12, but yeah.
Okay.
Yes.
So if I were to compare ISO server count performance difference between Ethereum chain and your RainBlock improvements in a geo-distributed manner, do you have that data? Let's say you
Yes.
32 servers
Yes.
and 32 miners in the previous.
Yeah. So I have like another one comparison. So this is the geo-distributed setting, right? So in the geo-distributed setting, we test the scalability of RainBlock. We use 4 miners that are in 4 different regions spread across 3 different continents, which is essentially the wide area network, which is very slow. Again, each RainBlock miner has IO helpers local to them, which are fully saturating the miner. And in this setting, RainBlock miners can process about more than 20,000 transactions per second, and they use about 32 servers. So we also increased the number of miners, but keeping them in the same regions. We just increased the number of miners, and we saw that they were consistently about 20,000 transactions per second. Overall, this work shows how a small percentage of extra hardware and careful designing of the architecture allows orders of magnitude improvement orders of magnitude of improvement in the end-to-end transaction throughput of public blockchains. So in summary, RainBlock builds on the main insight that it is I/O bottlenecks that limit the block size and not proof of work consensus. It avoids I/O in the critical path of processing transactions by introducing I/O helpers and storage nodes. RainBlock uses the novel distributed sharded Merkle tree data structure to reduce network traffic, and it can process about 20,000 transactions per second in a geo-distributed setting. So our work is open source, and you can check out the code base on GitHub, and you can please reach out to me with any comments or feedback. And thanks a lot for tuning into this talk. And now is a good time to ask any questions remaining.
So I think the general perception is that if you get rid of proof of work for something that's a lower overhead and oh, by the way, greener, that everything gets faster. So maybe that's not true. Your work is predicated on a different perception of the bottleneck.
Yes.
Have you run with a null proof to determine how much scaling they get, how much scaling you get? And also, I assume that if they improve the proof of something, if they improve the consensus algorithm, you'll be able to take advantage of that same consensus algorithm. Maybe you'll have to tune up the numbers of this and that.
Yeah, great question. So the question is if proof of work is supposed to be the bottleneck, is known to be the bottleneck, moving to a greener, much faster consensus protocol, it could improve the performance a lot. But there is prior work that replaces proof of work with an alternative consensus protocol and talks about how I/O is now the bottleneck, right? And what our work is showing is it's solving a much harder problem where even with proof of work, which is very slow, how much can you push the envelope by just alleviating the I/O bottlenecks in the setting?
Follow-on question.
Yes.
If using proof of something cheap, using an inexpensive consensus algorithm shifts the bottleneck to I/O, does that mean that your work facilitates the shift to a different consensus algorithm?
Yes. So our work could be compatible with different consensus protocols. Would it force people to move to a different consensus? Yeah.
No, not that. Does it make other consensus protocols that are less expensive, does it make them work
better?
Better.
Yes, definitely. So the whole work is about how the authenticated data structures which are used in public settings and the way they are stored on RocksDB or LevelDB have a lot of I/O amplification and redundant reads and writes, which fundamentally reduce the transaction processing rate. Even with a much faster alternative consensus protocol, the bottleneck is still going to be I/O bottlenecks, right? So far, even when they think about proof of work, folks have just looked at proof of work and have been looking at alternative consensus protocols. But we are like, even with proof of work, which has a rate limit, can we do some sort of batching optimization where you can pack more transactions, and that packing of more transactions is independent of what consensus protocol, right? Now, even in a, say, leader election, there is some sort of latency for one consensus round, right? And maybe miners have to pack all of the transactions that they can in a block in this latency. By using our work, you would just be able to pack more transactions into that block and achieve higher throughput. Any other questions? Please go ahead.
So I'm still trying to understand this time to durability aspect when you disaggregate your strategy. I have the intuition that if you have a light load condition, I think earlier miner was obviously storing it locally, and now it has to go over the network partition storage.
Mhm.
But under a heavy load, I can see basically it may just get washed.
Yeah. So if we think about the RAM cloud work, right? That was, I think, the first paper that talked about how, persisting it locally on SSD could be more expensive than doing it over the network, right? So doing a high speed in memory over the network. So also it's like a replicated storage. So as long as this block reaches one of the storage nodes, you can consider it to be durable, right? Now, this is the first thing, right? And then the second thing is also, even if you are adding more latency for this block to be durable in the storage node, over the network, you are looking at it from a throughput angle, right? Not from a latency angle. Under high load, lot of blocks being sent. And again, for a consensus round across all of the miners, it's going to take 10 or 12 seconds, which is the latency at which one block is being released in Ethereum network. At that latencies, adding a little more network overhead to get to one of the storage nodes is not going to show up. Any other questions? All right then. Thank you.